Alright, our next reaction of alkenes is the hydration reaction. And as you may have guessed based on the name, it is the addition of water. So if we start with an alkene, we add water to it. We add a hydrogen to one carbon and an OH group to the other side. But in addition to needing water, in general this reaction requires catalytic acid. Now, the mechanism here is actually highly similar to the hydrogen halide, the HBr addition that we covered just prior to this reaction. So you may recall in that reaction that it started with the alkene adding an acid that made a carbocation. The nucleophile attacked the carbocation, and then we formed the product. So we're going to see a lot of similarity in this reaction. So the catalytic acid is what gets attacked by the alkene. That forms a carbocation. The nucleophile now is not a halogen, but is instead water, which the lone pair on water can attack the carbocation, which gives us this intermediate, which loses a proton to form the product. Now, what is it that triggers the loss of this proton? Well, it's probably water coming in and acting as a base and removing that hydrogen. But so the first thing we want to note that's important, and as you notice, the acid here we say very specifically is catalytic. Now, hopefully you remember the definition of a catalyst from general chemistry, and that a catalyst is a species or a reagent that speeds up a reaction but is not consumed by the reaction. So if a reaction has a catalyst, one thing we should be able to find in its mechanism is we should be able to find that that catalyst is being used as it is in the first step, and then we should find in some subsequent step that it's being regenerated. And so that's what we see here. The acid is used up in the first step, but it's reformed in the last step. So the net is that the acid's not consumed by the reaction. We have as much of it as we ended with as we did when we started. Second piece of this reaction is, given that it goes through a carbocation mechanism, is this a Markovnikov reaction? So the first step was the alkene attacked the acid. That's going to give us a choice of two carbocations, less substituted or more substituted. We know more substituted is more stable. Water then attacks the more substituted carbocation, and then we regenerate our catalyst. So as you can see, the hydroxyl group, the OH group, which we could think of as being similar to the X group, ended up on the more substituted carbon, and the hydrogen ended up on the less substituted carbon. So that would count as a Markovnikov process. Now, one of the other things I like to do as we're studying these reactions is to give you some examples of where you might see a reaction like this. Now, these specific examples you don't need to memorize, but these are applications. Where do we see these reactions? And with a reaction like hydration, that's pretty easy to find examples of. So I'm going to show you two of them. The first one is ethyl. If we take ethylene and we heat it up with phosphoric acid and water up to about 250 degrees Celsius, we make ethanol. And this is how thousands and thousands and tens of thousands of liters of ethanol are made every year in industry for use in labs. But maybe a more interesting one to you is the following. So here's almost a carboxylic acid. It's not a carboxylic acid because the two hydrogens are missing. But if you add water to this alkene, you get an OH added to one carbon and a hydrogen added to another carbon. What is this reaction? Why is it significant? On the right, we have fumarate, and on the left we have fumarate, and on the right we have fumarase. And this is one of the steps within the citric acid cycle. Now, there's one major problem, though, with this hydration reaction, and it's this. First of all, we have to use strong acids, and second, high temperature. Doesn't always need 250 degrees Celsius, but it usually requires some amount of heat. And once you start using high heat and strong acids, there's a lot of things that you might not want to happen that can sometimes happen. And so we need milder conditions in many cases. As you can see, there are still plenty of cases. We can easily make ethanol from this reaction. But once your molecule starts to get more substituted and more functional groups show up, you have to be more careful about your reaction conditions, because a strong acid, not only will it react with an alkene, it could react with an aromatic ring, it could react with most carbonyls, including esters, amides, ketones, aldehydes. And so, as long as the alkene is the only thing you have, the acid-catalyzed hydration probably isn't too bad of a reaction. But as molecules start to get more complicated, then we start to run into issues. So while this might not seem like the best solution, but the most common solution is to use a reaction known as oxymercuration. And why do I say that might not seem like the best solution? Well, this is a reaction that's going to use mercury. And so you do generate mercury waste from this reaction, which is not necessarily a good thing. But the good news is it should do the reaction that you want and give you the products you want without completely destroying the starting materials that you start with. So in an oxymercuration reaction, again, we need our alkene. And we use mercury acetate along with water. So this OAC, I'll just draw out its structure over here. Basically, it's acetic acid missing its hydrogen. And then in a second step, that's why we put this 2 here. This 2 indicates that we don't just add all of these at once. We do the first part, we add the mercury acetate in the water. And then in the second step, we add sodium borohydride, NaBH4. Now this will give us the same result as the acid-catalyzed hydration. It gives us an alcohol, and specifically, it gives us the alcohol on the more substituted carbon. All right, how does this happen? Well, we're going to look at part of the mechanism, but we can't look at the whole mechanism, and I'll explain why in a moment. But in the first step, this mercury acetate basically falls apart. It dissociates. And it gives us a mercury cation with one of the acetate groups still attached, plus the other one no longer with it. But this positively charged mercury that we've now formed can be a good electrophile for the alkene to attack. Now it forms this slightly unusual looking three-membered ring with a mercury in the middle. And as we've learned before, three-membered rings are highly strained. So what does a three-membered ring want to do? It wants to open back up. Well, we need a nucleophile to do that. And that's what the water here can do. But where is the water going to attack? Well, we have a three-membered ring that's positive. And we know that carbons are electron donating. So both of these carbons here and here are donating electron density to the positive charge. Well, of those two carbons, which one is going to bear more positive charge? It's going to be the one that's more substituted. So the water attacks that more substituted carbon of the three-membered ring and breaks the ring open. From here, this acetate anion that was released can come in and remove this hydrogen to give us the neutral OH group. Now, this is the point where this first part of the reaction stops and we would add the sodium borohydride. So sodium borohydride is a reagent that we'll see more of in organic too, but it basically functions like H-. And what the H- will do is that it's going to replace the mercury group with a hydrogen. Now, how does that step occur? Well, recall that I said we weren't going to cover all of the mechanism of this reaction. This is the part that we're not going to cover. And the reason we're not going to cover this is because we don't know how this step occurs. It's believed that it likely goes through some sort of radical pathway, but as of now, in 2020, the mechanism of this reaction is still not all that well understood. Now, another thing that we can do with this oxymercuration reaction is instead of just making an alcohol, we could make an ether. And the way that we could do that is that instead of using water as in the reaction, we can use an alcohol instead. And the second half with sodium borohydride is the same. So the first part of this reaction starts in exactly the same way. We get our dissociation of the mercury, which allows us to form the three-membered ring. But now, with there being no water present, water can't be the nucleophile. And instead, methanol is, or whatever alcohol we would choose to add. It's still going to add at the same position. Opens up the three-membered ring. And then our oxygen cation can lose a proton. Finally, just like before, we add sodium borohydride to swap out the mercury group for a hydrogen. So by replacing the water in this reaction with an alcohol, instead of making an alcohol as the product, we've made an ether. Now, where could we run into a reaction like this? So, with the involvement of the mercury, this is obviously something we're not likely to see biologically. It's a reaction that's more likely to be used somewhere in a lab. But here's an example. So if we take this alkene and have it undergo oxymercuration with methanol, so we know that we're making an ether here. We get the ether formed at the more substituted carbon, and then this acetate group actually gets removed and converted back to an alcohol in this reaction as well. This just then needs to undergo a couple of additional steps, and finally we get to a final product. That looks like this. And what have we made here? This compound is known as methoprene. And where do we find methoprene? We find methoprene as one of the active ingredients in Frontline, which you may be familiar with as a common flea treatment for pets. Now there's one major problem with these hydration and oxymercuration reactions. Because these are both Markovnikov reactions, there's no way to make a primary alcohol in any of these reactions. Because for any alkene, the primary alcohol is always going to be the less substituted alkene. So what if we wanted the less substituted alcohol? Is that something we can make? The answer is yes. We just are going to need a different reaction. And so for that, we need hydroboration. And to talk about hydroboration, which is one of my favorite reactions, I spent several years doing research with the hydroboration reaction. But when we talk about hydroboration, we really can't talk about it without mentioning this guy, H.C. Brown. He actually won the Nobel Prize for all his work on hydroboration in 1979. But I think the pretty remarkable thing is, I believe he published his first ever paper on hydroboration chemistry in 1939 and continued to publish on hydroboration until, I believe, 2002, when he was about 90 years old. So what is the hydroboration, and why does it allow us to do something different? So the hydroboration will take an alkene and first treat it with borane, which is usually loosely coordinated to a solvent such as THF, tetrahydrofuran. And then in the second step, we add hydrogen peroxide and base. And as a result, this reaction gives us the less substituted alcohol, which we could call the anti-Markovnikov process. So the hydroboration reaction and the oxymercuration reaction are, we would call them complementary processes, because one allows us to form the more substituted alcohol, and one lets us form the less substituted alcohol. So how do we make that determination? And why is it that borane forms the less substituted alcohol? Well, again, this is something that we can explore based on the mechanism. So the first thing we need to remember about boron is less electronegative than carbon, or hydrogen, more importantly. And so if we're looking at BH3, the hydrogen is partially negative and the boron is partially positive. So recall, of course, that it's the more substituted position that can have more positive charge. So the more substituted position is the one that the hydrogen is going to be more attracted to. Now we also want to consider the fact that in this reaction, the addition of boron and hydrogen is actually simultaneous. So boron, having that empty p orbital, is a good electrophile, and the pi electrons of the alkene can attack the boron. Simultaneously, the boron-hydrogen electrons attack back to the carbon. And so in that one mechanistic step, we get the boron minus one of its hydrogens on the less substituted carbon, and the hydrogen on the more substituted carbon. But because this boron still has hydrogens on it, it's going to keep reacting. And it can add another molecule of the alkene. And as long as it still has hydrogens, it can do it a third time. To give us a boron where now all three hydrogens have been used up and the boron is now bonded to three carbons. So, is there a way to stop this addition? at what we would call the monoalkyl borane, which is this structure, or the dialkyl borane. And what those terms mean, monoalkyl borane, so a borane with one carbon group, boron with two carbon groups. Well, if you can figure out a good way to do it reliably, that would be a very, very useful thing. In fact, that's what I actually spent 2 years doing research on, was trying to get one of these reactions to dependably stop at this point. Turns out it's very, very difficult to do. But once you have that trialkyl borane, that's when we add hydroxide and peroxide to it. And as a result, we cleave all three of these carbon-boron bonds to get the less substituted alcohol. So again, hydroboration is another hydration type reaction. It adds water across an alkene. The key difference is that while acid catalyzed hydration and oxymercuration both give us the Markovnikov product, or the more substituted alcohol, hydroboration gives us the opposite, the less substituted alcohol.